Hey everyone, this is lesson 832, Ratios of Similarity. So on the previous lesson we talked about area ratios. We're going to look and explore a little bit more of that today in this lesson. And we're going to add to that perimeter ratios as well. So there's going to be, in this first problem, we're going to look at three different pairs of similar shapes. So the first is going to be a pair of rectangles that are similar, and I'm gonna help us fill in this little table of information. It's going to help us understand a little bit of how these ratios are related. And then we're going to do the exact same thing with a pair of right triangles. And then we'll do the same thing again with two isosceles trapezoids. So that's where we're going to start. So just to kind of give you an idea of what is coming up in this first page of notes. All right, so let's start with this first pair of rectangles. So what we're trying to do is organize our ratios of sides. First thing is we have a ratio of sides, a ratio of perimeters, and ratio of areas. Now, if we know the areas, then we could just make a ratio of it. Ratio just means a fraction. If we know the perimeters, then we can make a fraction of the perimeters. So it's really key that we find our area and perimeter. So this will be a reminder of some older topics so that we could generate these ratios. The third is the actual ratio of sides that we've talked about before. All right, so looking at these two rectangles, let's start with the ratio of sides. Now we want to match up corresponding sides. So I've kind of already highlighted using the same color. We have our left side of the rectangle has a 6, and we have this other left side of the bigger rectangle. We don't know its measurement, so we can't use those pair of corresponding sides. But the base of these rectangles, which are corresponding, we do know. So we could use those two measurements to write a ratio of sides. So there's a couple ways to write ratios, depending on whether you're going from small to large or large to small. We already know these shapes are similar. We're just trying to figure out how are their sides proportional or not. So we're looking at the way this table is organized is with a small figure on top and the large figure on bottom. So that's what's going to be consistent across the whole table. So since we're talking about sides, I'm going to take a side measurement, which is 15, and 25 is the large figure. So I'm just going to put 15. I'm going to put 15 over 25. All right, so this is our ratio of sides. Now, we want to reduce it if possible, so that's why I kind of put it a little bit to the left, because I want to make room for a reduced fraction. So does 15 over 25 reduce to? So what does that reduce to? So what number goes into both 15 and 25? It looks like 5 goes into both of these. So if I divide both of these by 5, what does that give us? So it looks like this is going to give us 3 over 5. All right, so our ratio of sides, we could say that a ratio of sides is going to be 3 over 5. Okay, so that was easy. We didn't have to do much calculations besides reduce that fraction. Now, to do ratio of perimeters and ratio of areas, we're going to first look to see at calculating the perimeter and area of these two rectangles. All right, so perimeter, for those you need a reminder, perimeter means we're just adding up all the sides around. So if I add up 6 plus 15, plus these two other sides. Do we know these other two sides? Well, because this is a rectangle, we know the opposite sides are congruent. So therefore, we do know all four sides. And so that should add up to, all right, if I actually calculate the perimeter of the small, I'll put S for small, is going to be 6 plus 15 plus 6 plus 15, which equals to, I believe that equals to, what is that, 2142? All right, so that's 42 units for the small one. So I'm going to put 42 units. I don't know if these are inches or centimeters. I'm just going to put units. And what is the perimeter of the large rectangle? Well, if we start to add up all four sides, you'll notice that we only have one side, right? We don't even have the other measurements. So we have an issue here, right? So we need to solve for a missing side. So let me move this out of the way a little bit. All right, so let's say if I put, let's call this X for this missing side, because it would be really nice if I had that measurement. We know enough to solve for this. We would set up a proportion to see what X is. So when we've done this in the past, the way we've set this up is we would match corresponding sides. So for example, X and 6 would be corresponding, right? X and 6. And that means 25 and 15 would be corresponding. So I would do equals to 25 over 15. All right, so that means we have a way to solve this. So when we solve this, this should give us, let's see, I believe that's 150 over 15, which gives us 10. All right, so that means X equals to 10 in this picture. So both of these sides would be equal to 10, where the top would be equal to 25. All right, so if we're going to add up all those sides, this is going to be what, 25 plus 25. Let me write that out. So perimeter of the large shape is going to be, I'll do 10 plus 25 plus 10 plus 25. And so that equals to, what does that equal to? So that's 50, 60, 70. All right, so we have a perimeter of 70 units. Okay, so that's a little reminder of finding missing sides of similar shapes and a reminder of perimeter. So this is kind of going to be a review of a variety of stuff. And then next is ratios of perimeter. So a lot of times when we get to this part, students are lost. Like, I don't know how to do that. Well, technically, we already did it. We already have the ratios. So all we need to do is write it as a fraction. So I'm going to put 42 over 70, and there's our ratio of perimeters. So the question is, does that reduce? How small of a fraction can we reduce this to? Any ideas? Okay. Well, if I look at this, I notice I have a 42 and I have a 70. I always happen to remember 6 times 7 is 42. So I'm just going to do a little bit side work here. So I know 6. I'm going to do 6 times 7 happens to be equal to 42. Does 6 or 7 go into 70? I believe 10 times 7 equals to 70. All right, so that means 7 goes into both of these. So then we could reduce this fraction to, 6 over 10. All right, so then at that point, you might look at it and say, can I reduce it a little bit more? Always check easy numbers. If I see an even number, I always check to see if I could cut it in half, divided by 2. So 6 divided by 2 happens to be 3, and 10 divided by 2 happens to be 5. All right, so we've reduced it as much as we can, and so our ratio of perimeters, if you notice, is 3/5, which happens to be the exact same thing as the ratio of sides. All right, well, that kind of makes sense, because to get the perimeter, all we had to do was add up all the sides. So literally, perimeter is all the sides together. So it kind of makes sense that these two, sides and perimeters, would have the same ratio. So the question is ratio of areas going to be the same? Well, we kind of already went over this in the previous lesson. And so if you don't remember, let's see if it comes out to be the same or not, or what is the connection. So if you already know, you might be able to tell me what the ratio of areas is just by looking at our ratio of sides. All right, so let's start with area of the small shape. So if you don't remember how to find area of a rectangle, we're looking at multiplying. I'll put it over here. Area of the small is going to be equal to 15 times 6. All right, so what's 15 times 6? I believe that's, let's see, 60 plus 30. So that's 90. So we're looking at 90 units squared. So I'm going to put 90 units squared. All right, and area of the large figure. All right, so we're looking at multiplying. Area of the large is going to be 25 times 10. Well, that equals to 250 units squared. All right, so 250 units squared. All right, so there we just had to multiply two numbers. So if I'm looking for the ratio of areas, I'm just going to write a fraction. So I'm going to take those same measurements and I'm going to put 90 over 250. Try to squeeze that in. All right, let me rewrite that. Looks sloppy. So 90 over 250. Now, does that reduce? Well, I noticed they both end in zeros. That means they're divisible by 10. So I could write that as 9 over 25. Now, does that reduce? 9 over 25, that one does not. Right? That one does not reduce. All right, so the question is, how does that ratio of areas relate to the other ratios? So we have 3/5, 3/5, and 9 over 25. All right, so 9 over 25. So see if you can remember that connection that we made last time. So I'm not going to mention it now, but I'll mention it maybe when we get to the next problem. All right, so we filled in our table. We're just kind of gathering data. We're gathering information, and then I'll kind of summarize it when we're done. All right, in the meantime, we're getting some good review of some prior topics. All right, so let's do B. All right, so same idea. We're just looking to work with a new shape. So this is a right triangle. Hopefully you notice it's a 30, 60, 90 triangle. All right, we see the 60-degree angle, which means we have 30, 60, 90. I've already kind of highlighted the sides with colors so you can see which ones are corresponding. You'll notice that we only have one measurement given in both of these, but because it's a 30, 60, 90 triangle, we should be able to calculate the missing sides of both triangles. All right, so I'm going to just kind of go through this part quickly. If you if you need help remembering how to find missing sides of special right triangles, I suggest you look back at your notes on that topic or rewatch the video from, I believe it was chapter 5, maybe 5.1.1 or 5.1.2 lesson. All right, so since I know the short leg of this triangle is 6, right away that tells me that the hypotenuse is going to be twice as big. So I know this is going to be 12. And I know the long leg is going to be 6 times the square root of 3. All right, so that's what I know on this one. So if I use kind of the same logic on the smaller triangle, I know the hypotenuse is given to us here. It's 4. Question to you, if you could tell me, what does the short leg equal to? Now keep in mind this picture has been rotated, so don't assume everything's in the same position. So if the hypotenuse was 12 here, the short leg was 6. On this one, the hypotenuse is 4, so the short leg is going to be what? All right, if you say 2, you would be correct. All right, so that's a 2 that goes there, which means the long leg is going to be 2 root 3. All right, so we have all the sides. Ratio of sides, we could use any pair we want. I would probably choose the smaller numbers. In this case, I would probably choose maybe 2 and 6. 2 and 6 are corresponding sides. They're both short legs. So let's do, we're starting with a small figure on top. So small figure would have a 2, and the large figure is going to have a 6. All right. Does that reduce? Of course it does. So this reduces to 1 over 3. All right. So we figured out the ratio of sides. Now, can we figure out the other ratios without even calculating the perimeter area? Now, if you remember from the previous problem, we saw that ratio of sides and ratio of perimeters was the same. Now, is it always the same? All right. And so the ratio of areas was definitely different. So I'm gonna guess that this ratio of perimeters is also going to be 1 over 3. All right. So let's see if that's true. I'm going to kind of do this one. Let's do perimeter of the small one. We're going to add up all the sides. So 2 plus 4 is 6 plus 2 root 3. Now those I cannot add together, so I'm going to leave them like that. And the perimeter of the large, I would add up 6 plus 12. I'll just do that together. That's 18 plus 6 root 3. All right, so I'm going to put those in my table. 6 plus 2 root 3 and 18 plus 6 root 3. Now, we're supposed to make a ratio of perimeters of those. Now, that's definitely something that looks a little bit confusing. What I'm going to do is, to make this a little bit easier, I'm going to rewrite these so that maybe they have something in common. So what I do know is I could factor out a number here. I'm going to factor out a 2, and that's the same thing as 2 times 3 plus the square root of 3. And on this large one, I'm also going to factor out a number. I notice this number 6 actually goes into 18, which means I'm going to factor out a 6, and this is left with 3 plus the square root of 3. All right, so I notice here those 2 root 3 and 2 root 3 are the same. So what I'm left with is actually 2 over 6. Okay, so if I actually treat this as a fraction, those two portions kind of go away. They reduce to a 1, which means this fraction reduces to 1 over 3, which is exactly what I expected. I was hoping it was going to be the same, and it was. All right, so I feel pretty confident. Hopefully you feel very confident knowing that those two ratios will always be the same. What will the ratio of areas be? Okay, well, let's see. If we're going to find the area of these two shapes, let's start with area of the small one. Well, this is a triangle, so this is going to be 1/2 base, which is 2, and the height, which is 2 root 3. All right, so that's how you would find the area of the small triangle. And that simplifies to, the area of the small is 2 root 3. Oops, I forgot my units on my perimeter. Units. And so this one's going to be units squared. And then the area of the large triangle is going to be 1/2 6 times 6 root 3. All right, so I believe that gives us an 18 root 3 units squared. All right, so I'm going to put that in my table. So I have 2 root 3 units squared, and I have 18 root 3 units squared. All right, so when we write our ratio of areas, this is going to look like 2 root 3 over 18 root 3. Does that reduce? Well, you should notice they both have a square root of 3. So those would reduce and go away. So I'm left with 2 over 18, but I believe that also reduces to 1 over 9. All right, so I did not get 1 over 3, but I got 1 over 9. So how are they related, right? So this ties, so some of you probably already knew this coming into the lesson because we talked about it on the previous lesson. If you didn't quite understand it last time, let's talk about this. So if you know, here's the last two ones we just did. If you know the ratio of sides is 3 over 5, then what you could do is take that ratio and square it. So what happens when you take 3 squared, right? It gives you 9, and when you take 5 squared, it gives you 25. Right, so this fraction, this ratio of areas was really, I don't know if I could fit this here. So it was really the same thing as 3 over 5 squared. Okay, so does the same thing apply to part B? 1/3, if I take 1/3 and I square it, does that equal to 1/9? Well, it does. Okay, so then what does that tell us? That tells us we didn't really need to find the area to figure out what the ratio of areas was. All right, so that tells us maybe when we do this next problem, maybe we could find a way to not have to find the areas here, or at least not all the work. So let's start with the basics. Let's do ratio of sides. So I'm going to ask you to tell me what this one is. What is the ratio of sides? See if you can figure out which sides to use from the small and which one to use from the big. All right, if you said 5 over 40, you were correct. You just have to reduce it. So if you reduce it, this should equal 2. What's 5 divided by 5 is 1, and 40 divided by 5 is 8. All right, so now that I know the ratio of sides, my second question to you is going to be, what is the ratio of perimeters, right? Without even calculating the perimeter, can we determine what the ratio of perimeters is? Okay, you tell me, what is it? All right, if you said 1/8, you would be correct. All right, and so the last ratio, if you could tell me, what is the ratio of areas then? All right, so if you said, if you did the calculation of 1/8 squared, you would get 1/64. All right, so 1/64 would be the ratio we're looking for. All right, so we didn't have to calculate area or perimeter for any of these, but if I know one of these area and perimeters, I could use the ratio to help me figure out what the other one is. All right, so that's what we're going to practice next. So I'm not going to work out the perimeters and areas on this one, but if you would like to do that, then I would say pause this and go ahead and try to work it out and see if it comes out to these fractions. But because we have some more examples to go through, I'm going to kind of go on to the next. All right, so a type of question you might get, here's to kind of review a little bit of what we just did. So common shapes are a little bit easier to do. So rectangle, triangle, trapezoid, we have formulas to calculate areas and perimeters. But weird shapes like this, we might not have a good way to calculate areas. So here's a type of problem where I know all the measurements of one shape. There's a similar shape, but I don't know any of the measurements. And I know the perimeter. Because I know all the measurements, I could calculate the perimeter, which is 37 centimeters. The larger one, I don't know the perimeter because I don't know any of the side measurements. So you might say it's impossible for me to figure out what the perimeter is. But some additional information that says, well, I know the area of the small shape is 100 centimeters squared, and the area of the larger one is 900 centimeters squared. How can I use that information to help me find the perimeter without having to go and measure everything about this larger shape or calculating all the side measurements? So let's look at the basics of what we know. Do we know linear ratio? Do we know perimeter ratio? Do we know the area ratio? All right, so those are the first things I always think about in a problem like this. So linear ratio would mean I know sides from both shapes, which I don't. So linear ratio is it's questionable at this point. We don't know enough. Perimeter ratio, well, I have one perimeter, but I don't have the other, so it's kind of hard for us to get a ratio using only one number. But I do happen to have enough for an area ratio. So let's use that information to help us. So let's do, because in the previous examples we kept doing small over large, let's just keep it the same. So if I have the small area, if I use a small area, which is 100 over the large area, which is 900, we reduce this will give us 1/9. Okay, so now we have an area ratio. Now that we have an area ratio, which should be familiar to you, we just kind of saw this. My question to you is, what is the perimeter ratio? Can we work backwards? All right. Well, since I know this 1/9 is really the same thing as 1/3 squared. That must mean that perimeter ratio is 1/3. Right? And I also happen to know that linear ratio is the same as perimeter ratio. So those would end up being the same. All right. Now the problem wasn't asking to find all these. They're just asking what's the perimeter. Well, this is how you're going to solve it. So instead of us doing tons of measurements, what we're going to do is I'm going to put, since we don't know perimeter, I'm going to use perimeter as x. And what I do know is if I want to solve for x, I need a ratio. So x over 37. X over 37 was the perimeters. So then I look at my choices, which ratio should I use to put as the second fraction? Should I use linear ratio, perimeter ratio, or area ratio? So while linear ratio is the same as perimeter, so I'm going to narrow this down for you. Are we going to put 1/3 or are we going to put 1/9? So you tell me. All right, if you said 1/3, you are correct. So we're going to put 1/3, and at that point, now we could just solve this. We could cross multiply. So this would be 3x equals to 37, and then we could divide both sides by 3. So x is going to be equal to, what is this? I think that is 12.3. 3 repeating. All right, if I did that calculation correct in my head. All right, so that's a way we can find the perimeter of a shape, odd-looking shape. It's probably impossible for us to find it any other way. All we did was use what we understood about ratios of areas, perimeters, and sides. So side ratio is our linear ratio, and those are always the same as perimeters ratio. And to find area ratio, all we have to do is square it, and that gives us our new ratio. So, all right, one last problem before we go, and that is just to verify if two shapes are similar. So maybe we're not trying to find a missing area or missing side. I just want to know if these two shapes are similar. They look the same. For sure they look the same. But are they similar? Well, let's start with the basics. We have some side information according to the picture. We have some side information from both shapes. And it looks like the area was given for both of these. So I have sides on both and areas on both. That tells me I have enough for linear ratio and area ratio. So we'll stick with small over large on this fraction. So what is the linear ratio of these two shapes? And reduce your fraction on this one as well. Okay, if you said 7/21, then you are partially correct. You need to reduce this. So this would be 1/3. All right, so linear ratio is 1/3. So then what is the area ratio? Well, I've kind of give you a hint here. Linear ratio squared. So 1/3 times 1/3 is going to give us 1/9. Okay, so we've calculated linear ratio and area ratio. We still haven't figured out if the shapes are similar. So the last question says, does 40/360, which is the two areas, so this is kind of a ratio of the areas, does it equal to the ratio area that we just calculated? So does 40 over 360 equal to 1 over 9? Oops, question mark. All right, do those two fractions equal to each other? You tell me. All right, it appears, so if you did this correctly, it looks like those two are the same, right? 40 over 360, that reduces to 4 over 36. 4 over 36, which reduces to 1 over 9. All right, so 1 over 9 equals to 1 over 9. All right, so those two figures are similar because those two fractions equal each other. If it was not, if it was like 41 over 360, then it would not reduce to 1 over 9, and they would not be similar figures. All right, so that's an example of a type of question you would need to be able to do. You'll notice it's not a lot of calculations. It's just about understanding how the shapes are related to each other. All right. Hopefully you understood at least 60% of what we went over today. Major idea that you should really get out of this is how the ratios are related. So side ratio, perimeter ratio are always the same. Area ratio is always going to be side ratio squared or perimeter ratio squared, right? So that's the huge thing. That's going to tell us which fraction to put in this equation. So if I'm talking about if we had areas on one side, then I better use the area ratio. If I have perimeters, then I use the perimeter ratio. If I have sides, then I'm going to use the side ratio. So here's your collection of options. You have to decide which fraction you're going to use. All right. That's all for this lesson. Let me know if you have any questions. And that's it.